Yeah, I guess we can start. As usual, we can start with questions from last time. So first thing, so we've been talking about the following. It's about the existence of test modules. And there is this general principle that, so the existence this boils down to prove that, so if if this is a pure, so implies irregularity generically. So somehow that irregularity always holds generically. So let's just say this, and C is irregular. Let's see, put C on a C whose principal open sees all generic points, or in other words, for C avoiding all minimal primes. So C avoiding, well, C in R, all minimal primes. Okay, so this is the general picture that you need to keep in mind of what existence means. And so any such a C is called a test element. And so that's why you see that the existence of test modules is equivalent to proving the existence of these test elements, right? Even in a pure module, you have to prove that there exists a C. This is the case, so it's proving that there exists a test element. Okay. So this has a few implications, right? So this led to do a few reductions. So, well, in what I wrote, use a localization, right? So you're looking at a neighborhood of generic points. So this means that you can always shrink R. You can always replace R by RC, improving that this is a ratio, right? So, and you see the geometric intuition. Why this means shrinking? What you're shrinking is the spectrum of R, right? Spectrum of R contains the spectrum of R localized at C, right? This is the principal open DC inside here. And as soon as C avoids all minimal prime, that means that this principal open will see all generic points. So you can shrink R as much as you want. And in doing the shrinking, what can you do? You can go ahead and say that R is a normal integral domain. Because R is a finite, right? So the regular locus is open. And it is reduced to, right? Because it is a pure. So you can say that all generic points are regular. And so you can find an open neighborhood around all generic points, all minimal primes that is regular. And so by shrinking and shrinking and shrinking, the first thing you can do is assume that R is a normal, but it's a regular domain sort. And so in this case, all you need to do is to prove that there is a C that is non-zero. But actually, if you put here C equals 0, it's empty. So, and moreover, this N is finally generated, right? Well, at the generic point, at the minimum point, well, that's a field, right? So it is free, and so it is free around an open neighborhood of the generic points, meaning that it is generically free. So you can shrink and shrink and shrink until N becomes free, right? So you may say that N is isomorphic to R here in some Belly number that we call mu, right? So these are the two standard reductions you get to do here. Super standard. If you go and look at any proofs, historic proofs of the existence of this set of objects. So the other day, we also argue that we may assume that C is finally generated. That was a different type of reduction, right? And I don't know if you guys remember that I was talking about two different lemmas to do so. And the first one is the only one we need. So definitely, I look at it and yeah. So I think so. I was taking that information from a paper of Manuel Blakela when he gives this argument. And I was looking into the wording, and he says like, okay, one can always say that C is finally generated, and here are two different types of arguments to see that. So I thought both were necessary, but no, just one of them. And actually, for the proof we're going to present today, I don't see how to use this actually. So I must admit that I think we wasted our time trying to argue that C can be taken to be finally generated for what we're going to do today. But I think in the spirit of his paper, he's just trying to find simple reductions on this existence because the full existence is still open. So I think part of his argument is like, okay, these are all the assumptions you can do to help you proving existence. But I don't, for what we're going to do today, I don't think that's necessary. You can tell me if I'm wrong in the proof I'm going to present. Okay? But then from now it's going to be a curiosity that you can assume that C is finally generated. Because of what we're going to do today. So let's see. Where is it? So this condition here. We're going to call this condition here being generically irregular. Right? It means that more geometrically that there exists a dense open subset of this spectrum of R over which you have regularity. That's it. Okay. So, or on which we have regularity. So this is the proposition we're going to start with. Proposition. Let's take MC, be pure over R. I'm going to assume it's a regular domain. And I'm going to assume what I just said. I'm going to assume, first of all, that, well, let me say such that N is free. Okay? And I may assume that C is finally generated. But I don't think I need it. I'm going to put in parentheses. That's the proposition for Manuel's paper. Now here we're going to have at least two hypotheses. Okay, suppose either, so suppose either that mu is 1. I mean, this really means mu equals to 1, right? Like if n is 0, there is really nothing to prove. Okay, the 0 module is a regular. So that, in other words, suppose that M is isomorphic to R. So this is the classical case, right? Because this is going to tell about the singularities of R. It's a Cartier algebra acting on R. So this is arguably the most important case. Or B, let us suppose that C is principally generated. Okay, so this is the case in which we have a Cartier module of the form M, comma, P, P, and so on. We have one single action, right? Yeah, then the conclusion is that comma C in either case, so I'm put an or here, in either case is generically regular. As a corollary, right? Let me just say it works. As a corollary of M of C exists if M equals R or C is principal. Well, actually, if in general, if M well, it also follows here. Like I'm gonna let you do this. Like if M is an ideal, if you need it. What matters is that M is generically isomorphic to R, so it can be an ideal. So let me just put M equals R. If this, I'll let you play with more general cases. Okay. And as I told you, another case in which we know this exists is if R is an algebra of finite type over an infinite field. But I won't do that proof here. I'm already tired of all these cases and stuff. So, how does this work? So as I was saying at the beginning, yesterday I was looking at the proof and I got stuck at it. So yeah, there are a few things when I was saying that I don't quite understand. And so I'm trying to fix that. I sort of came up with an alternate proof. But I think this proof it looks like it's morally speaking the same proof, but just expressed in a different way. At least it makes me understand it better. But even in Manu's argument, I definitely don't see why we would use this. Because, like, in the principal case, of course, it's going to be generated with one element. And in this case, you can always reduce to that case in which you have something, one element actually. So, the argument I'm going to present for this is as follows. So, proof. What I'm going to do is I'm going to start explaining why A implies B, why we can reduce it to A. So claim B can be reduced to A. Or in other words, A implies B. Well, not that mu equals 1 implies that, but if I prove A, I prove B. Sorry, if I prove the theorem assuming A, I prove it assuming B. Okay? Yeah, I guess I'm just dumb to write that A equals B. Let me just delete that. So How does it work? So let's look at the hypothesis B. It means that we have phi in here, right? This is the Cartier module structure. Right? But n is 3. So this equals and so by the direct or universal properties of direct summands and I guess direct products. So this is direct sum, this is direct product. I wrote direct sum, but when I define it, it's the same as the direct product, right? The category modules. So this thing here is equal to this. I guess I should write mu times mu. It's the same thing as for y a linear model between three modules. It's a matrix, right? Here it's going to be a matrix, but of maps, like. Okay. So, but I'm going to explain a bit more on how this isomorphism works. But like I can do it right now. So, what is the intuition behind this, right? An element here is going to look like a vector. So let's write it down like that. Let's write down as a column vector, right? The column vector of elements like this. Right? That's what an element in here looks like. And so to say where to send it, well, I'm going to send each of them to something. So let me say, and so this one is this one individual is going to go to a vector, right? So I take this one, I send it to something in here, but it's going to look like a vector. So it's going to have to look like a choice of elements here. So here I'm going to have phi. Let me just say phi. I have to do this properly. I think it's 1, 1. ER1, phi1, 2, R1, blah, 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 phi, me, sorry, 1, mu, this, sorry, 1, right? So I take this one and I send it to something that has to be a vector. And every single entry is going to look like this. It's going to be a map from here to here, right? I'm sending something that it looks like this, and the entry is in R, right? So it's given by a map like this. And so there, and then you continue like this, right? To the point that you happen to generate a matrix. So in here now it's going to be phi, now mu1, let me just write down R1, mu, phi mu, R, not R1, it's going to be Rn. So, or R mu like this. Okay? So, what I'm saying is like, since you have two free things here, a map from here to here is going to look like a matrix of maps. I have to choose, I guess, a matrix of maps. Square matrix of maps like this, right? And then I plug in my vector in here in this way. I take this one, I plug it in the first column, and what I get here is going to be Well, actually, so, and then, well, I guess this goes to this sum, right? But to decide where it goes, all I have to do is to choose this piece. Okay? It's not clear, so yeah, maybe I didn't do the best explanation. So, but it's literally the same argument as for why maps between free modules is a matrix. The only difference is the same argument, but when you do the classic thing, you don't have this, right? And what is formed from R to R? Well, it's an element of R, and that's going to be the entry of the matrix, right? That actually is just going to be multiplication. So if you do that the same argument here, what you're going to have are elements of R acting on those entries. But the action is like a vector thing. So I guess I could have written down like this is equal to this matrix of maps acting on that vector. I take this, I multiply by that matrix of maps, and I'm gonna spill out by the images, right? It's the same argument, just that in the classical sense here, you just have elements of R. Or you can think of the fees being of degree 0. But in general, you have like, I'm making something very simple, very confusing. It's the same argument as usual, okay? All I'm saying is that, quite abstractly, a map here is an element of here, but the intuitive way to think about it is that you're going to have a matrix of maps. Yeah. Okay, good. Okay. Or I just thought I wasn't appreciated. Well, probably was doing a very bad job on explaining it, but you still understood by your own. Okay. So the next thing I'm going to do is to cook up an actual matrix. So for this, let's come back to R for a second. R is regular. Okay. In particular, it is Gornian. Well, so actually what I have is that the canonical module, or I can take the canonical module of R to be R. Okay? So then I'm giving a map, I'm thinking that this is omega R, to the F upper shriek of omega R. And this map, it's definitely injective. So this is injective. So here, well, actually, I think I can write down this map very explicitly. So it. So well, so quite literally, this map that I have here is the choice of an element here. Okay? So this is a subtle part. All I'm gonna do so you guys remember. So Yeah. So you see the thing, right? Like, so I have to define a map. Well, a map from here to here, right, is the same as the choice of a mapping here, right? So it is equivalent to the definition of a map from here to here, which is another way to express the adjointness between upper streak and push forward. This map has to be adjoined to something there, but you can see that it's literally the same thing, right? So what I'm going to do is to take this map to be to be injective. So I'm going to choose an element here that it's just non-zero, but it's non-degenerate. So it's not killed by. So let's say I'm going to choose a map here that I'm going to call actually capital P. So you see that what I'm trying to define is technically speaking a Cartier operator on R, which is Gorentian, but a Cartier operator on R only exists if you can guarantee an isomorphism from here to here. You guys remember that? The Cartier operator only exists if existence is equivalent to an isomorphism from here to here. Because that isomorphism is going to manifest into a generator of this. Okay? And so what I'm going to do is this. I'm going to look at the generic situation. And so generically, let me call K the field of fractions of R. Very abstractly, these two things are isomorphic. In general, I can just put any field here. And these two things, sorry. I guess if I put a field here, I should have put L here. Well, technically speaking, I should have written this down here. Like, it's just a choice of that section. And so what I'm going to do is that I'm going to use that generically because I'm working with a field. I have a trace. Okay? And so I'm going to choose my map that sends R to something in here to be this. So this map that I'm choosing here is going to be a generic Frobenius trace. Fields are Gorenstein rings for which I can cook up a Cartier operator because these two things are isomorphic. I can always find an isomorphism from here to here. Okay? And so actually, since, let's say, like, since this is the same thing as K tensor with this, and actually the generator for that is just any element that is non-zero. It's going to be a generator. Because in a field, any element is a generator. Right? And so I'm going to choose it to be here. So essentially, I'm just choosing any non-zero element in here. And generically, it's going to generate. Okay? And so that's going to give me this injective map from here to here. When I send R to that, but I have no reason to believe that that phi generates this home set. All I know is that there exists a non-degenerate one. There exists one that is non-zero and is not killed by any element of R. By multiplication, it's torsion-free. It's torsion-free because torsion-free means being generically non-zero. Okay? That's the subtle part of the argument here.
Can you please explain this part again?
Which part?
Yeah, then.
So I need to cook up, and so in principle, I wish I had a Cartier operator for R. That's my dream. That's what I'm trying to cook up. That would entail to find an isomorphism from here to here. what I'm trying to argue is that I can find an injection, and that injection boils down to, since this thing is just that, I have to send 1 to something, to some phi, but that phi has to be generically non-zero for this to be injective. And so what I'm going to do is that I'm going to look at what is happening generically, and I get this equation. I can just localize the field of fractions, and in there I can find a non-zero element. Generically, it exists. Actually, that exploits that this is a finite. That this whole thing is non-zero, that this is a finite. If we're working with non-infinite thing, it may happen that this is 0 and there is nothing to cook up. It's crazy, but it's like that. So generically, I know that there's a map that is non-zero, and actually I'm going to choose it to be here. I'm just going to choose an element of in here that it's non-zero generically. That's all I'm doing. And actually, it's going to have to be a generic Frobenius trace. So all fields have Frobenius trace. So R is an integral domain, so I'm gonna use the Frobenius trace of that field of fraction and assign it to R. And so that's gonna give you an injective map from here to here. But to honestly cook up a Frobenius trace for R, I also need to be surjective, to have an isomorphism. Okay? I need this surjectivity here. This is the part of the Manuel's argument that I was very confused about, so I have to do it like this. How do I get the surjectivity? What is the thing I can do in this proof all the time? I can always shrink, right? So this too is injective, but moreover, is generically an isomorphism. Right? This is generically an isomorphism. So this co-kernel is torsion. This co-kernel vanishes when you localize at K, right? And so it means that it is killed by something because it is finally generated, right? Every single generator vanishes when you localize, meaning that it's killed by something that is non-zero. And so all of them are killed by something. And so the whole volume is killed by something that is non-zero. So what that means is that I can do this. So here I'm doing 1 goes to phi, and this is an isomorphism on, or when I do the base change by RC for some C different from 0 in R, of course. Generically, it's an isomorphism, therefore, there is an open neighborhood of the zero ideal where it is an isomorphism, because everything involved is finally generated. A finiteness again. Okay? So I'm going to shrink my R, if necessary, to guarantee that it has a Frobenius trace. Right? Because it's not true that every regular ring has a Frobenius trace. The existence of the Frobenius trace is an isomorphism. Well, in a Gorinstein ring would be, in general, of a Cartier operator is an isomorphism from here to here. And therefore, the Cartier operator, which in the Gorinstein case we call a Frobenius trace, is adjoint to this equality or to this isomorphism. Okay? Who needs to exist for the Frobenius trace or the Cartier operator to be defined. Okay? So there is this part in Manuel's argument that I don't understand, which I think is arguing that, but in a very strange way. Actually, he translates everything to sort of like a F module, so like a Leibnizian module type setup, and do some shenanigans there that I think are fine, but I don't quite understand. I think there are some few things that need to be explained. But let's do this. Okay. Okay, why am I doing this? Because, so let's say shrink R such that when you look at this, it's isomorphic to this. Yes. I.e., P is a frog trace. For instance, if we happen to know that R had a P base, well, that would be for free, but we don't know. It's an arbitrary regular ring at this point. Okay. Why am I saying this? Because in choosing this phi ij, this is the matrix of maps we had before. What can I do? I can now say that they are PE, and now I choose some generators for some unique elements here, right? Where now this is a matrix of elements in R. And moreover, I guess, and let you digest this. Now I understand very well the Cartesian structure on M. Shrink R, yeah, you see that. So, and moreover, we have this Cartesian structure in here. I claim that the Cartesian structure we started with, that we call it phi, I think. It's now given. It's now the following. This is going to be equal to this composition. So what I'm going to do is that I'm going to act linearly by this matrix. Let's call this matrix A. So let's say that A is the matrix Aij. It's of size n times mu times mu. So I'm going to act, I guess, by the Frobenius push forward of the matrix. Just forget the push forward and act linearly, like you learn in linear algebra. And then from here to here, what you do is that you apply phi entry by entry, right? Like here you can see that there is an ambiguity on whether there is someone goes or Frobenius goes, but everything commutes with everything. So there is no ambiguity. So what I'm going to do is I'm going to apply phi entry by entry. And that's the action. So this is the phi I was talking about. It's a similar story when I told you that any map from here, suppose that you don't have the mu, right? Then we know that any map from here to here, you first multiply by an element of R, A, and then you apply phi. Here I'm saying it's a similar story. You act by a matrix, and then you apply phi component by component. Okay? Now, here is the second part of Manu's argument that it was very confused about, but I think with this language now I understand what's happening. Now you look at this matrix, right? And so, okay, let's look at what is this project from here. We want, remember, what I'm arguing is why I'm trying to argue that I can assume that mu equals 1. So to do so, what I want to do is to take a determinant. Right? If you know, like if you have you know, map a linear map between vector or three modules, right? And you want to know whether or not it is objective or an isomorphism or so on, you can always say a determinant, and that's going to reduce it to the one-dimensional case. This is powerful thing from linear algebra. That's what we want to apply. But there is a chance that the determinant may be 0. Okay, and then we end up with nothing. Okay, so what that means is that when you look at this A, so this A may not be injective, may have a kernel. That can happen. But it's fine. We just need to do an extra assumption. So the next step is to argue that we may assume that this matrix is injective, that it has no kernel. Okay? So why is that? So let's look at A. So we have a map from R mu to R mu. It's fine for me if the map, if the A is not reflected. That's pretty fine. Because they can always shrink, right? But for that, I needed to be injected to start with. So that's the part of the argument in the paper that is very obscure. Actually, it makes a reference to a different paper, and you have to go to that paper, and it's a corollary of like a sequence of, it's super obscure. But this is what is happening. So, well, suppose it's not injected. So, well, that's fine. We can do the following. This one is injected with kernel A. So I'm going to replace in principle n by this quotient to this replacement. So this part of the argument, it's pretty fine. Like if I can prove that, well, first of all, you may notice that this doesn't have to be free, right? It can be whatever, right? But I can always shrink R enough to guarantee that it is free. So you can always shrink R to make sure that A is generically injected, if you will. Because otherwise, the Cartier module you started with is literally 0. So as soon as that's not the case, you can shrink R and assume that this is string. So shrink R once again to say that this thing here is string. And actually, you know, like the point is that if the kernel of A is there, the kernel of A is a Cartesian module of this, right? You see it because if it goes to 0, well, it contains 0, right? So it is a Cartesian module. Phi of the kernel of this matrix is a Cartesian module, right? So this quotient here, well, what I'm arguing in part is that it is a Cartesian module too. So it's a Cartesian quotient. And if I can prove that this is generically regular, so has to be the original Cartesian structure. Okay? So this part of the argument say that I may assume that this A here is injective. Because I can replace the original Cartier module I had by a quotient of it, which still sees irregularity. It's part of this nilpotency thing. Like this is an nilpotent Cartesian module. So I can just get over. I just replace this like Cartier module for one that is nil isomorphic to it, if you will, or yeah. And so irregularity is intact. Okay. So yeah, so there is this part of the argument though, that I really couldn't understand, but I think is really just can be argued like this. Okay, this part is very tricky. But so yeah, may assume or may assume that A may assume that A is injective. Okay. Actually, now I can see then that this is I need to take a determinant now. Well, it's up. Kind of do that. Okay. Now it is injective. It is an injective map in between modules of the same rank. R is a domain. So it's also generically surjective, right? By linear algebra. If I tensor by K, it has to be an isomorphism. I have something that is generically an isomorphism. What can I do to guarantee that A is an isomorphism, that it is invertible? I can shrink, right? Actually, I know what I have to invert. I have to invert its determinant. Now, the fact that A is injective, all I was trying to argue is that the determinant is not 0. And now what I do, I shrink IA by inverting exactly the determinant of this matrix to make it invertible. So replace R. So I need to make this localization by the determinant of A. So shrink R, shrink the space to assume A is an isomorphism. So I have an isomorphism of my module, and then I apply phi. In particular, I may assume that actually this argues that I can assume that this is my Cartier structure. Because this explains that the Cartier module I have with this map and the one I have with this one, in which P acts, component by component, entry by entry individually, is an isomorphism of Cartier modules. Okay. So that's it. May I assume okay, let me put it in this way. I.e., the Cartier module I started with was something like this. Is isomorphic to the Cartier module in which I add by phi component by component. It's a direct sum of Cartier modules. Right? Which is literally to take this one here remember, Cartier modules is an abelian category, so it's the direct sums of Cartier modules. And what do you think? The test module of a direct sum is the direct sum of the test modules. There is no rocket science behind that. So in other words, this one is a regular. So this one is a regular if and only if each of them is a regular generically. So, may I assume okay. Remember, because what we're trying to do is to prove generic irregularity out of an impure one. So all the obstruction to do so can go away if you shrink, and get to that. Okay? So let's prove the case mu equals 1. Actually, literally, here what we have to prove is that R with this Cartier structure is a regular. And it is. Actually, you can just do it directly. Actually, we won't do it here, especially because this is taking longer than I expected. It's always like that, right? It's going to be much longer than I expected. Actually, I'm gonna let you that. I'm gonna leave you that as an exercise to prove that a regular ring is a regular with that Cartier structure. So everything seems to boil down to the F regularity of regular rings, which I think we haven't even mentioned, have we? I don't know. So yeah, it's going to be an important exercise for you. Okay. Thus, we gotta prove that if we have a pair like this, so actually I'm gonna assume that C is inside CR, is a pure. If you have an impure pair, then it is generically regular. Well, it suffices for this. Assuming R is a regular. Which is the most important case for us at the end of the day, right? Oof, getting hungry. So how do we do this? Essentially, I'm gonna let you do this. Homework. So let's see how we reduce. So essentially, what I'm gonna do is that I'm gonna argue that I can say that C is essentially CR. Okay, so this work as follows. Or let's see. Are there any questions so far? Let me see what I wrote. So for this, we're going to do this. So this thing is a pure, right? So let phi e, or let me just say phi in here, CE, I guess, BAF splitting. Okay. So let's look at phi times R, right? I'm talking about the Cartesian algebra, like the submodule inside here, right? C, it lives in degree E, right? That's what I said. CE, right? Which lives inside CE, the full Cartesian algebra of R. But again, like by the same argument, I can shrink enough to calculate Frobenius trace. So I know that there is a Frobenius trace. Like this. So there's an inclusion from here to here. And this is injected because this is a splitting. Like I could have chosen 0, for example. I choose something that is splitting. And now you tell me, what can I do to guarantee that that's an isomorphism? I can shrink again, right? Because now this becomes a map from R to R. So I'm just choosing, well, this is the thing. I just know that, well, that's what I know, right? I know that phi equals the trace times something. You need to determine. Invert that. Then phi is phi e. So I can take phi to be the Frobenius trace. Okay? And so I can may assume that C is the Cartesian algebra generated by the phi. In the notation we use is this. In particular, I can assume its principal. And actually, that Frobenius trace because I can always shrink. That's just the key part of the argument. The key part of everything that matters is generic. So all obstructions to happen is just go away if you shrink enough. It's simple but brilliant. And I think according to what I hear, the rest is homework. I think there was a part of the argument in which you can also say that it's not necessary at this point, but I think you can assume that E is equal to 1 too. So we need to clear this as a regular. You see, it's almost the whole Cartesian algebra. I mean, it's true. So it's definitely true. But first of all, I don't think it's that much of an easy argument. Actually, I think I talked about this with Lorena in office hours at some point. That this is a regular, you can all if R comma T is a regular. One direction is trivial, this one. The other one is solved. You remember this, Lorena? It was an exercise in the service of test ideals. Actually, Lorena asked me an exercise that did the test ideal, but these two things are the same. It's true. And the reason is actually because they share the same delta. the divisor of phi to the e, the divisor of phi is the same, and that's the only data that matters about the map. Is what is its delta? What is its divisor? So you may argue that you can reduce to that case if you want, but I don't think it's necessary. You can prove in this particular case that this is regular actually. This is regular. You don't need to prove that it's generically irregular. It is irregular, just like that. Okay, this is irregular. Because regular rings, where regularity implies irregular. I'm gonna let you do that as an exercise. Take that the Frobenius is free, right? And irregularity means that you can split an element eventually, and so on. You already have those propositions, and so at this point it's very simple. Just prove that a regular ring is irregular, and that finishes the proof. Okay. So it's this proof that the existence of test modules boils down to proving that regular rings are irregular. Okay. Oof, that was cool. I think I don't think it makes sense to continue this topic. I think we can stop here. It's hot and we're hungry, at least I'm hungry. But next time we're gonna continue with the following. So far what we have proved is the existence of test elements. There is a stronger notion of test element that I like to call principal test elements. And its existence requires a little bit more work, but I think I would like to go through that because those are very important elements. And so next time we're going to work on the existence of principal test elements, which are much stronger than just test elements. Okay. So, for example, any element, let's say any non-zero element of a test ideal is a test element, but in principle, test elements are test elements, but they are much stronger. But you can say that the test, we're going to prove that the test ideal is generated by principal test elements. That's an important thing. Okay, see you next time. Bye, Lorena.
Bye.